Topic 12.3 deals with the transmission of electrical power. So, how do we get the electrical energy from the place where it's generated to the places where it's used, our homes and businesses? And it's important to realize that just like in any other system, when we are moving electricity, when we're taking electrical energy from one place to another, there's going to be a loss of energy. The system isn't perfect, and so along the way, energy will be lost. And there are a lot of ways a lot of places where that can occur. The first is just through the resistance in the wires. And as the current passes through the wires, it's going to have a heating effect, and so you're going to lose electrical energy as it gets converted to thermal energy. And that has an effect, but we can minimize it by using thicker wires. There is a maximum to how thick of a wire you can use, though, because think about it, those wires also have to be held aloft by the electrical poles and by the large towers you can see in this picture. And if they're too heavy, then they're gonna collapse under their own weight. They won't be able to be held up. But they can also use specific materials which have lower resistances, so the metals they use play a big part. There's also losses that are called dielectric losses, and this is where we actually lose energy into the material that's surrounding the metal. Some of the energy actually gets transferred into the insulation. I mean, there's nothing you can really do about that. And then the other part is there's actually small fields that get generated within the wires from the electrons. You have these electrons moving through the wire, and they create magnetic fields, and those magnetic fields interact and interfere and actually slow each other down as it moves along the edges of the actual conducting wire. We also have energy losses in the transformers, and the transformers are where we actually step up and step down the current, or we change the voltage, or we increase the voltage or decrease the voltage. The biggest places where energy is lost here are in eddy currents, and eddy currents are where you get those those forces that are opposing the change in the magnetic flux, like we talked about before. If you remember Lenz's law, we've said that the currents are going to create fields that oppose changing the magnetic flux, and that actually happens here. And so those are acting against the movement of the coils, and it creates almost like a braking effect within the generator. Again, there's the resistance of the wires and the windings. There's this effect that's called hysteresis, and really it's kind of like a residual magnetism that's left over as it goes around each turn, as the coil of wire spins. As it comes back around the next full cycle, there's still a little bit of this magnetic field left over from the previous one that affects it. You get flux leakage if the coils aren't wound tightly enough. And then just the conversion of energy to sound and mechanical. If there's any type of shaking or any noise in the actual generator itself, that's coming from the electrical energy. It's being converted from the electrical energy, and so you have losses there. And there is a little bit of electromagnetic radiation. You have moving charged particles, and anytime you have moving charged particles, you have electromagnetic radiation being generated. So even though you do have these losses, they're very minimal at this point. The transformers and the wire systems that we have now are about 99% efficient, because there's been a mix of materials used, because the systems that have been developed are extremely efficient. One of the ways that they've decrease some of the dielectric effects and some of these other impacts is to have a silicone core, and they're developing new alloys that have lower resistance and that minimize some of these other effects. Just for economic reasons, there's really no ideal value of voltage for electrical transmission. It's just whatever is appropriate. Power is generally generated at about 11,000 volts. And then for transmission, it's stepped up to about 765,000 volts for AC and 880,000 volts for DC. And the reason for this is because remember that voltage is really the energy per charge. And so if we have a higher energy per charge, we need fewer charges to transmit the same amount of energy. And what we find is that the energy that's lost in the wire is less if we have a high voltage low current than if we have a low voltage high current. And part of that is just the resistance. If you have a much higher current in the wire, you're going to have a much higher resistance, and so you're going to lose more energy that way. If you have a very, very, very high voltage and a very small current, then you can get the same amount of power much more efficiently and without losing nearly as much energy because of the resistance in the transmission lines. And so those really, really tall high voltage electrical energy lines, the current through them is fairly low, but the voltage in those lines is incredibly high, which is what makes them so dangerous. And our transmission lines actually have 3 conductors in them that are carrying current. And those 3 conductors, if you remember that with our AC, the current is actually rising and falling in a cyclical nature as that coil spins around. The voltage is maximum in one direction, and then it drops to 0, and then it increases in the opposite direction and drops to 0. And so this oscillation can actually hinder or can actually have an impact in the transmission of the electricity. And so what they started doing is to have these 3 lines, and the three lines carry currents from 3 different generators that orient themselves perfectly with their oscillations to make the most efficient transmission of electrical energy. And so after the current goes through the transformer, it's stepped up to a very high voltage, very low current, and it's generally transmitted into a supergrid. And the supergrids, they're all nationally connected, but they're focused in regions. And then as the electricity comes into a specific city or town, they go through a series of stepping downs. And you can actually see the big green boxes that are sometimes out front of people's yards, or the cylinders that are on the electrical poles. Those are actually step-down transformers, and so they're taking the current that's in the power lines and stepping it down to an appropriate voltage for individual houses. Before it gets to that, the current travels through larger substations where it's stepped down from that really, really high voltage to a kind of a medium voltage. That medium voltage current is then passed through the power lines into neighborhoods and into communities and areas like that. And then from there, it passes through those smaller those smaller transformers that you can see to the voltage that we get in our houses. And so they they step it up to a very high voltage, very low current for transmission over long distances to minimize the energy lost. Then as it gets to cities, they step it down one notch. As it gets to neighborhoods, they step it down a little bit more. And then once it gets down to the house level, it's stepped down to the voltage that's at our plugs and outlets. Now, when you have transformer transmission problems, this is a series of equations that you're going to be using. These top three deal with the power in transmitted electricity. Okay, we have the average power is equal to the root mean square of the EMF times root mean square of the current. That's our first one. Hopefully these are just, you're familiar with these. Second one, the average power is the resistance in the wire times the square of the root mean square of the current. And the third one is average power equals the square of the root mean square of the EMF divided by the resistance. And remember, these are just our P equals VI, P equals I squared R, and P equals V squared over R, applied specifically to AC electricity, to AC power conduction. And we have to use the root mean squares, again, because of the cyclical nature of alternating current power transmission and generation. Our second set of equations here are our transformer equations. Okay, and this gives the ratios. So the voltage in the primary, the potential difference in the primary set of coils divided by the voltage or potential difference in the secondary set of coils is equal to the number of coils in the primary over the number of coils in the secondary. And that ratio is also equal to the current in the secondary over the current in the primary. And then, of course, we have our good old reliable V equals IR. And between those basically 5 equations, you should be able to solve any transformer transmission problem you're presented with.